So welcome everyone to the Applied Algebraic Topology Research Network seminar. The title of the talk today is Morse-based fibering of the rank invariant, and we have two speakers, Robyn Brooks and Celia Hacker.
Hello everyone. Thank you for coming to our talk. So as Sarah said, Robyn and I will be presenting the work that we've been collaborating on for the past year. So this is a project that has started about a year ago at the Women in Computational Topology workshop that was held in Canberra. And the project was led by Claudia Landi, and then the other members of the group are Asileta Bapat, Barbara Maller, and Elizabeth Stevenson. And then the goal of this project was to use discrete Morse theory as a way of, to help in computations of multi-persistent homology. Okay, so throughout the talk, first we'll start by introducing multi-persistence modules and the rank invariant. And then we'll follow with some notions of discrete Morse theory that we will be needing in order to, for you to understand what we've been doing in the project. Finally, so the largest part of the talk will be about how we've been combining discrete Morse theory with multi-persistence, and we will show two results that we have obtained during the past year. Okay, so most of you already know what single parameter persistent homology is. So quickly, we start with a data set, and we obtain from the data set, we obtain a filtered complex. That is a filtration along one parameter, and then we obtain the persistent module, which then we can visualize with what is called the barcode or the persistence diagram. And then this has been widely used in TDA, but it would be nice sometimes to be able to use multiple parameters in order to filter the complex to highlight different aspects of the data set. So this is why we introduce multi-parameter persistence. So the pipeline goes kind of in the same way. We start with the data and we obtain this time an n-filtered complex and the corresponding n-parameter persistence module. In this case, the output we will be looking at would be a persistence space, which is the higher dimensional analog of the persistence diagram, or the rank invariant. But the output is not as, so it's more difficult to compute n-parameter persistence than one-parameter persistence. And the output is really the rank invariant and the persistence space are really summaries of the data set. And then one visualization tool that you might want to remember is Rivet. So this has been introduced by Lesnick and Wright. And this is a tool that allows to study 2D persistence modules. And they use lines to kind of slice the module and restrict it to 1D persistence. And what we'll be doing is a bit in the same flavor. So we'll be looking at how to restrict the modules to lines in the parameter space, but using discrete Morse theory to determine which lines we want to look at. Okay, so now let's go a bit more in details of each of these steps. So the first step would be the multi-parameter filtration. So in this case, we are always looking at a finite simple shell complex K, and we will have a parameter space that is Rn, on which we have a post-it structure. So we say that some points U and V in Rn, so U is smaller or equal to V whenever each of its coordinates are smaller or equal to the coordinates in V. And then for each of these values in Rn, we obtain a subcomplex of K, which we denote Ku. And according to the post-it structure, whenever U is smaller or equal to V, then the corresponding complex Ku is included in the corresponding complex to V, so Kv. And then we ask that the union of all the simplices, all the subcomplexes form the complex K. And moreover, that every simplex has exactly one entrance value in the filtration. So by this, I mean that if we are looking at a parameter space R2, if the simplex enters in the filtration at the value 1, 0, and it enters as well at the value 0, 1, then it has to be present at the value 0, 0 of the filtration already, as 1, 0 and 0, 1 are not comparable in the poset structure. And this, the entering at only exactly one value in the filtration, we call this being 1 critical. So we say a simplex is 1 critical in this case. So now that we have the n-parameter filtration on the simplicial complex K, we will obtain the multi-parameter persistence. So this is n-parameter persistence module we will denote this by V throughout the talk. And this is a collection of modules such that for each value in Rn, we have a module that we don't call VU, which will be the homology of the corresponding subcomplex Ku for a fixed homology dimension. And then on top of that, we also have the morphisms between each of these modules VU. And these are the morphisms that are induced in homology by the inclusion of the subcomplexes Ku and Kv. And this is defined also whenever U is smaller or equal to V. I've also talked about the rank invariant already. So the rank invariant is an invariant of a persistence module. And it's a map that is defined on pairs U and V such that U is smaller or equal to V. And it takes values in N. And then it's defined as being the rank of these maps that we've seen earlier, the maps that are induced in homology from the inclusion of these subcomplexes. Just a side note, the rank invariant is, if we restrict to 1 parameter persistence, then the rank invariant is equivalent to the persistence diagram. Okay, so this is all we needed to know for multi-persistence. We will now jump to discrete Morse theory. So discrete Morse theory has been used already in persistent homology and multi-persistence as well. For example, you can see some papers by Claudia Landi and collaborators. And discrete Morse theory has been used mostly to reduce the size of the complex that we're looking at. Because, as I've said, the computation of multi-persistence can be very computationally expensive. So the discrete Morse theory is used to reduce the size of the complex to a complex with less cells, but the same homology. We'll choose a slightly different direction for our project, but you will see this further in the talk. So the ingredients we need for this, for our talk, would be a discrete gradient vector field, which is also sometimes called acyclic partial matching on the simplicial complex K. And this is a pairing of the simplices such that whenever 2 simplices are paired together in the discrete gradient vector field, one simplex is a facet of the other simplex. And so we can see in the illustrations below that the paired simplices are denoted by the blue arrows. And then we ask as well that there are no cycles in the matching. So for example, if we're looking at this complex here, then we do see a cycle, namely these blue arrow, the 3 arrows that I'm circling in yellow form a cycle as they, you can think of a cycle on a graph, but for simplicial complexes, in a pairing of higher dimensional simplices, this would be going from a K simplex to a K+1 simplex back to a K simplex and arriving at the starting simplex again, always following pairs that are connected by the fact that they share a face. Okay, and then you can see as well that some simplices are marked in in red. So for example, this one here. And this denotes the simplices that are unpaired in the matching. So in the case of a discrete gradient vector field, like we have here on the left, we call these simplices critical. And then in a discrete Morse vector field, discrete gradient vector field, sorry, every simplex is either in a unique pair or it will be critical. So it can at the same time.
Question, what's the geometric intuition behind using the word gradient? What's the function that I'm taking partial derivatives of? Why are you using the word gradient?
It comes from, well, it comes from the analogy with like smooth Morse theory. But yeah. I don't know, Robyn, do you have an intuition behind this? Because I have to, the smooth case, I don't have
Yeah, so you can see these arrows, right? These are kind of the analog of arrows in a smooth vector field, where this is kind of like the flow on the simplicial complex. And these critical cells, they're analog in the smooth case. These are essentially like points in manifolds which have zero derivative. So they're going to be like saddle points. In general, like these vector fields come from a function defined on a manifold. So you can kind of think of this vector field as like a flow on the manifold of that function. Does that make sense?
Okay. Okay. We'll see. Thanks.
Okay, cool. Well, okay. So I've mentioned earlier, so we want to tie discrete Morse theory and persistent homology. So let's see how we can do this. So we're given a simplicial complex K, which has both a gradient vector field V and an n-parameter filtration. And we will ask that this gradient vector field is compatible and the filtration are compatible in the following way. So that is to say, when we have a pair of simplices, sigma and tau in the vector field, then they always have to be at the same step in the filtration. So they enter at the same value of the filtration and they stay throughout the filtration, they stay paired throughout the filtration. And so whenever, okay, so that's what happens to paired simplices, but now what happens to, yes?
Okay, so there is one question from Steve. Do you think so I don't understand the no cycle rule. Doesn't the pairing always increase dimension? If so, how can you come back to where you started? Like maybe you can explain just the cycle rule again.
Okay, yeah, let's go back to this. So the reason why we don't want cycles overall is that so the discrete gradient vector field ultimately will allow us to collapse the simplices collapse simplices along the gradient vector field to only keep the critical cells. And so this will allow to have the complex with the same homology type, homotopy type as the starting complex. And so, for example, if we we collapse pairs of simplices along the arrows. So if we try to, so in the case of the discrete gradient vector field, if we collapse everything like this, then we will end up with just a point, okay? But then if we try to collapse here along the cycle, well, all of the edges around the cycle will collapse to the same point, ultimately, creating a homology class in dimension 2. Okay, so that's why we want to avoid the cycles. Is it, I don't know if this is clear.
There haven't been further questions, so.
Okay, well, just don't hesitate in case. Okay, so yeah, so we want the paired simplices to appear at the same time in the filtration, and then whenever, and then it doesn't matter when the critical cells enter the filtration, but the time where they enter the filtration will be called the critical value, okay? So maybe an example to illustrate this. So now we would be working in R2. So R2 would be the parameter space, and here each box represents a step in the filtration, and we see the corresponding that are added and the subcomplex that we have at each step. So if we look at the first box here, we see that 2 vertices are added at the same time, but no edge is added, for example. So in this case, both of these vertices are critical. But then if we move to the following box here, then we have a pair of a node and an edge, and they, as you can see, enter at the same time. And so so the critical cells remain critical throughout the filtration. We've just kind of marked them in a lighter orange so that we really highlight where they enter, and then they just remain there. And so the discrete gradient vector field remains the same throughout the filtration. So it's a fixed discrete gradient vector field on the complex. Okay. And so now I think Robyn will tell you how we can use these critical cells and why we want to use them.
Thanks. Screen. Okay, great. So yeah, let's talk a little bit about how we can use this discrete gradient vector field to kind of talk about how we can use this to understand the homology of the n parameter filtration. And in order to do this, the critical values, these values in the parameter space where critical cells enter the filtration, these are really important to understanding the homology groups of the filtration and therefore the rank invariant. And why is this? Well, so maybe this will give you guys some intuition like why we want to use this discrete gradient vector field. There's a really nice theorem in discrete Morse theory which tells us that every pair in the discrete gradient vector field essentially defines a simplicial collapse which preserves the homotopy type of the subcomplex. Okay, are there questions? Sorry, I see my chat going on. We're good? Okay, so let's look at these 2 simplicial complexes from the previous filtration that we had. We can see that these 2 simplicial complexes differ by a pair of simplices in the discrete gradient vector field, right? Namely sigma and this edge sigma and its vertex tau. Well, what the discrete gradient vector field is really telling me is it's saying, if I follow the arrow of the vector field, right? I'm pointing from my facet to my simplex. This gives me a deformation retract of the simplicial complex, which maps tau and sigma onto the other boundary components of sigma and preserves the homotopy type, right? So the discrete gradient vector field is saying, if you follow this arrow, just take the vertex tau, take the edge sigma, and smush it down to the other boundary component of sigma, and you're going to get, you know, the simplicial complex with the rest of the discrete gradient vector field, just less sigma and tau, essentially, okay? If we wanted to do that again, right, we could collapse both of these edges here, which are also paired in the discrete gradient vector field, again, following the arrows of the discrete gradient vector field. So this says I can take this vertex and this edge, map them to this vertex, do the same thing here, take this vertex and this edge, map it down to this vertex. That vertex is critical and so is that edge, so I can't collapse anything else. And I'm going to get a simplicial complex that looks like this, just the disjoint union of a point and a circle, okay? So essentially discrete gradient vector field prescribes simplicial collapses which preserve homotopy type, right? And if 2 subcomplexes are homotopy equivalent, then they're gonna have isomorphic homology groups, okay? So what does this tell us about our filtration? Well, if we have 2 steps of our filtration which do not have isomorphic homology groups, this means that the associated subcomplexes are not homotopy equivalent, right? The discrete gradient vector field then tells me that, well, these two subcomplexes, they can't just differ by pairs in the discrete gradient vector field, right? Because otherwise they would be homotopy equivalent. Therefore, they must differ by critical cells in the discrete gradient vector field, okay? And I'm talking about comparable steps in the filtration. So we can use the critical values in the parameter space, right? The entrance points of these critical cells in the discrete gradient vector field into my filtration to try to identify steps of my filtration, which might have different homology groups than the steps that immediately precede them. Okay, cool. Oh, okay. So since these critical values are really important to us, for every filtration and compatible discrete gradient vector field, we want to define the set of critical values as C, right? This is just all critical values of the filtration with respect to V. Since our simplicial complex K is finite, right? And since this filtration K is one critical, meaning every cell has a unique entrance value, we know that C is also going to be finite. Okay, so let's try to find in our example the set C. Okay, so we have this bifiltration here. We're kind of thinking about it as superimposed over R2, right? And the critical cells of the discrete gradient vector field defined on our filtration enter in the yellow highlighted squares, okay? And so the associated parameter values of these yellow highlighted squares are going to be all the critical values, okay? And sometimes we refer to like the associated subcomplex as a critical step in the filtration because it's the subcomplex that we have at a critical value, okay? And so you can see, right, in this filtration, let me get my highlighter, right? The steps of the filtration, which immediately precede any yellow square, they do indeed have different, they're gonna have different homology groups than the subcomplex in a yellow square, right? So these critical values are kind of identifying spots in the filtration where we have a change in homology group. But if you look at this square here, right, it turns out these critical values are not enough to identify every spot in the filtration where we see a change in homology groups, right? So this step in the filtration here has different homology groups than the steps in the filtration which immediately precede it, but it's not associated, it's not a critical step in the filtration, right? It's not associated to the entrance of a particular critical value of the induced discrete gradient vector field. All of the critical cells in this discrete gradient vector field are already have some lower entrance value in the filtration, namely here, here, and here. Okay. So in order to capture all of the information about all the points in the filtration where we see a change in homology groups, we need to close this set C under least upper bound, and we define this closure as C bar. Okay, and just kind of an abuse of terms, we sometimes say that C bar is the set of critical values, even though it's the closure of the set of critical values, and we sometimes refer to points in C bar as critical values, even though not all of them are going to be critical in the way that we defined earlier, right? In particular, right, we'll have some points in C bar which are in C, which means that at those steps in the filtration, we have the entrance of a critical cell into the filtration. But the points in C bar minus C, meaning these things in the closure of C, which are not critical values, these indicate a step in the filtration where two or more critical cells appear together for the first time in the filtration. Okay. And of course, since C is finite, C bar is also going to be finite. Okay. So let's look now at the set C bar, right? We've closed this set under least upper bound. The least upper bound of these two critical values is this value here, right? And we can see, again, like we did earlier, this indeed is a spot in the filtration where we're going to see a change in the homology groups from the previous steps in the filtration. And where that change is coming from is the fact that, well, this critical, let me choose a color that might actually show up. Right, this critical cell entered here, these two critical cells entered here at values which are incomparable, right? I can't compare these two values in our poset structure. However, this, right, is the least upward bound, and it's going to be the first place where we see all of those critical cells together. So in terms of the filtration, we may indeed see a change in the homology groups at this step. Okay, cool. So this is what C bar looks like if we're actually looking at the filtration. If we just want to view C bar in the parameter space, we're just going to see a set of points closed under least upper bound. So sometimes it's beneficial for us to look just at the parameter space and not kind of at the parameter space with the filtration superimposed over it. Okay, cool. So since C bar is essentially a set which contains all parameter values where we might see a change in the homology groups of the filtration, we want to use C bar to basically completely recreate the rank invariant for any pair of values in the parameter space. So how do we do this? Well, the first thing we do is for every value in the parameter space Rn, we want to associate a unique critical value, which we call U bar. And this critical value is going to be the maximal critical value, which is less than or equal to U, okay? So this is one of the things that's kind of nice to view in the parameter space, right? If I have a point U, I want to look at all points less than or equal to U, that's everything in that gray square, and then I just look for the maximal critical value less than or equal to U, so we can see that U bar here is going to be C2, right? This is going to be unique because we've closed C under the least upper bound, right? And you can see that I've defined it here for all parameter values where the associated simplicial complex is not empty. The reason we do this is if we do have a parameter value where the associated simplicial complex is empty, well, the empty simplicial complex has trivial homology groups, so we kind of understand what those homology groups look like as well, right? If we go back to thinking about the filtration, what are going to be the properties of the associated subcomplexes Ku and Ku bar? Well, really importantly, these subcomplexes are going to contain the same critical cells, right? U bar is the maximum critical value less than or equal to U. So no critical cells can enter the filtration between these two steps of the filtration, right? Since U and U bar are comparable, we know that Ku bar is a subcomplex of Ku. But again, because no critical cells can enter between Ku bar and Ku, we know that Ku bar differs from Ku only by pairs in V, right, in the discrete gradient vector field. And this is exactly what we want because this tells us that there is then a series of simplicial collapses we can do to get from Ku to Ku bar, right? So we have a homotopy equivalence between these two subcomplexes, which means that they then have isomorphic homology groups. Okay, so just as an example, let's see this on the level of the filtration, right? So, oh, I don't want that to be green. Okay, so if this is Ku, right, we've already seen that the associated U bar for U is this critical value here with associated critical step in the filtration Ku bar, right? And we already saw previously that these two subcomplexes are homotopy equivalent precisely because they differ only by pairs in V. If we look here at Kv, well, the point in C bar, which is maximal and less than V, is going to be this parameter value here. the associated simplicial complex is KV bar. And again, like we can kind of see that the discrete gradient vector field shows us exactly how to do simplicial collapses to get from KV to KV bar. We take this edge and this triangle, and this discrete gradient vector field tells us that we can map this edge and this triangle to the other boundary components of the triangle. So that's one collapse. Then we don't have this triangle anymore. We have this edge paired with this triangle here, and we do the same thing. We map the edge and the triangle that this edge is a face of to the other boundary components of the triangle, and we get down to KV bar. Okay. Cool. So it's these nice properties of U bar, and their associated critical steps in the filtration that allow us to prove our first theorem, which tells us we can completely determine the rank invariant from this set C bar. So here's the statement of the theorem. If we have a finite simplicial complex K with an associated nice filtration curly K and a compatible discrete gradient vector field V, okay, then for like a fixed homotopy degree, if we want to compute the value of the rank invariant for U less than V in the parameter space, well, the value of the rank invariant between U and V is going to be equal to the value of the rank invariant between U bar and V bar, okay? And this is if the associated subcomplex KU is not empty. If it is empty, then the rank invariant is just going to be 0. Okay, cool. So if I want to figure out the rank invariant of a pair, I just look at the rank invariant of the pair of the bars. And we'll do a really quick proof by picture. And basically just kind of put together the steps of the proof that we essentially just talked through, right? So if I have KU, KU bar, KV, KV bar, okay, right? KU and KU bar contain the same critical cells, same with KV, KV bar. Same critical cells, because of the discrete gradient vector field, implies homotopy equivalence. This homotopy equivalence induces isomorphism on the level of homology. So we know that these two, these pairs here have isomorphic homology groups, right? And since the rank invariant is just the rank of the inclusion map on the level of homology, right? If I have isomorphic homology groups, then I'm going to have equivalent rank invariant. Okay, are there any questions? No. Okay. Okay, great. So once we basically were able to recreate the rank invariant from this set C bar, we wanted to look at using this set C bar in computing the rank invariant by fibration. Oh. So what do I mean by this? Well, Celia kind of mentioned it on the first slide, but it's known that essentially the rank invariant of an n parameter persistence module can be understood by slicing that module by lines with positive slope, okay? So what you're doing is essentially you're taking an n-dimensional problem and you're slicing, fibering the parameter space with these lines with positive slope to get a one-dimensional problem. Okay, so if we go back to this slide here, right, we have a two-dimensional filtration. If I draw a line with positive slope here, right, I can see that this line picks up essentially a line in the filtration. So if I restrict this filtration to that line, I'm going to get a one parameter filtration. So for every line with positive slope, I restrict my filtration to that line, I get a one parameter filtration, and then I can create the associated persistence module called VL, right? The persistence module restricted to this line, okay? And in particular, if I have 2 points in Rn, I want to compute the rank invariant of those two values. Well, I can take a line through those 2 points, create filtration restricted to that line, create the persistence module of that filtration, and the rank invariant associated to the restricted persistence module is going to be the same as it is in the n parameter persistence module. Okay, cool. So the other reason that like fibration is beneficial, fibrating the persistence space to understand it using essentially one-dimensional persistence, is that a lot of these lines through the parameter space are going to have equivalent persistence diagrams. In fact, you only need a finite number of representative lines with positive slope to basically pick up all possible persistence diagrams of lines in the parameter space with positive slope. Okay, and this has been done before by Lesnick and Wright. They determine representative lines using Betty tables, and their method of determining these representative lines is only valid for 2 parameters, right? An important thing when you're doing this fibration is you need to make sure that you have enough representative lines that you capture all possible persistence diagrams of lines in the parameter space, right? So our goal kind of then became, we wanted to use this set C bar in discrete Morse theory to determine equivalence classes of lines, equivalent in that they have equivalent persistence diagram, which works for any number of parameters, not just 2 parameters. Okay, so we're gonna tell you how we make these equivalence classes, but first I need to introduce a couple definitions. So if I have a point U in Rn, the positive cone of U in Rn is just all points greater than or equal to U. And in particular, the boundary of this positive cone decomposes into disjoint faces. So here in R2, there are 3 disjoint faces to the boundary of the positive cone. U, the vertex itself, this blue line here, which is all points in R2, which have same x value as U, but greater y value. And then the last boundary component is this green ray here. It's all points in R2, which have the same y value as U, but larger x value, okay? And we're particularly interested in how these positive cones interact with lines with positive slope. Which leads us to a definition that we use a lot, which is something called the push of a point onto a line. So if I have a line with positive slope, I have a point U, well, the push of that point onto that line is going to be the intersection of that line and the boundary of the positive cone of that point, right? So since L has positive slope, this is going to intersect the boundary of the positive cone at exactly 1 point. And you can kind of think that here we're taking this point U and we're pushing it along the boundary of its positive cone onto the point L. Okay, so why do we want this? Why do we want to push points onto a line? Well, we're going to use this push to recreate the persistence diagram of L from C bar. Right, so if this U were a critical value in my n parameter persistence model, right, that means it's associated on the level of the filtration to the entrance or the entrance of a critical cell or the entrance of several critical cells in the same subcomplex. If I want to know where those critical cells will enter the filtration restricted to L, well, the one criticality of the filtration tells us if the critical cell enters here, it has to enter the filtration restricted to L exactly at push L U bar. Okay. So what this means is, right, we know from the n parameter situation, right, that C bar completely determines where the filtration has a change in homology groups. This is going to be the same for L, except for we need an associated set, essentially the push of L of C bar, right, the set of critical values onto L. Okay, so if we look at this picture here, right, C, these are my critical values, meaning they are associated to critical cells entering the filtration. If we push these onto the line L, right, we get the following 3 points. You can see here C4 and C2 push to the same point, right? But the idea is that no critical cells can enter the filtration restricted to L between these pushes, right? And we may have critical, or we do have critical cells entering at these pushes. So the persistence diagram is going to be completely determined by this set push C bar onto L. Okay, so in view of this, Celia is going to tell you now exactly how we define the equivalence relation of lines of positive slope in the parameter space.
Okay, so let me share my screen again. Okay, so now we have all this machinery of the pushing the values onto the line L, and we have the U bar, and we will use these things to create equivalence classes of lines, and then we will see the last theorem of the talk. So the way we define the equivalence classes of lines, so first we want to define what it means to be in the same reciprocal position with respect to a point U. So by this we mean that whenever we have some lines, two lines L and L prime, we will say that they're in the same reciprocal position if they intersect the boundary of the positive cone of this point U on the same face. So in this case, all three lines L, L prime, and L double prime intersect the positive cone of U along the vertical boundary face. Okay, so they're in the same position. But for example, if we had taken a line here, so this new line that I drew in black would intersect the boundary face of U, of the positive cone of U along the horizontal axis, or horizontal boundary face. So it would not be in the same reciprocal position as U, as L, L prime, and L double prime. Okay, and now we can define the equivalence class, the equivalence relation of lines using the critical cells. So we say that two lines L and L prime are in the same equivalence class, or they're equivalent, if they're in the same reciprocal position with respect to all of the points in the critical set. So all of the critical values. So we can see here that, so the critical values are still C1 to C4. And this time we have the same lines, but now L and L prime are in the same equivalence class, whereas L double prime is no longer in the same equivalence class, because now L and L prime both intersect the positive cone of C2 along the horizontal boundary face, but L double prime intersects this the positive cone of C2 along the vertical face. Okay, so we have two different equivalence classes here. Okay, so how do we use these equivalence classes? Well, they allow us to partition the set of all possible lines in the parameter space into a finite set of equivalence classes. Finite because we only had a finite number of critical values. So we can go on to our very last theorem now. So we are given two lines L and L prime with their corresponding parameterizations, always lines with positive slope. And if L and L prime are in the same equivalence class with respect to C bar, then we know that if we restrict their diagrams to, if we restrict the diagram of the module to both L and L prime, and this is how we denote it like this. So we know that there is a bijection between the diagram of the module restricted to L and the diagram of the module restricted to L prime. And on top of this, we also know how to go from one diagram to the other. So by using the bar operation and the push operation. Okay, so we will see a few steps of the proof very quickly. So as Robyn has said earlier, the diagram of the module restricted to L is completely determined by where the critical points are pushed onto that line. Okay, so if we're given a point ST in the diagram, we know that it will correspond to a pair of points CI and CJ in the the push of C bar onto L. And then we will use the fact that the sets push of C bar onto L and push of C bar onto L prime are in bijection to obtain the points in the diagram of V restricted to L prime. So let's see how this works. Okay, so again, we have here our lines L and L prime that are in the same position with respect to all of the critical points that are denoted in black here. And we see C1, C3, and C1, C2, and C3 are the pushes of the critical values onto L. Same for D1, D2, and D3. They're the pushes of the critical values onto L prime. And the bijection goes as follows. So C2, for example, will be sent. It will be sent to, sorry. C2 will be sent to D2, C3 will be sent to D3, and C1 to D1. Okay, and how is this bijection obtained? Well, C2, as we know, is obtained from pushing a critical value onto L, so it corresponds to a critical value. So for this, we would use the bar notation. So the critical value it corresponds to is C2 bar, which is the closest critical value that is smaller or equal to C2. So first we send C2 to C2 bar, and then we want to obtain a point on L prime. So this time we use the push. So we push C2 bar onto L prime, and this is how we obtain D2. Okay, so using this bijection between these two sets, we can obtain the corresponding points on the line L prime. Since we've seen already that pretty much what happens along these two lines in the same equivalence class is that the filtrations have the same steps and we have the same changes. So basically the diagrams are in this. The diagram are in bijection, and so how do we obtain the points S prime and T prime in the diagram restricted to L prime is by using the parametrization of L prime. Okay, so that's it for the proofs. I've told you how to compute from points in the first diagram, how to obtain the points in the second diagram. And what is nice in this theorem is that it really allows us to partition all the possible lines in the parameter space into a finite set. And then in each of these finite set, if we select one line, then we can always, then we know how to compute the diagram along each of the other lines. So it really allows us to reduce the number of lines we're actually interested in to compute the rank invariant along. Okay, so we have some objectives for to continue this project. So one of the things I would like to highlight is that this framework is valid for any number of parameters. So we do not have to restrict to 2 parameters, and we will use everything that we've built here to be able to compute the matching distance, which is a distance between 2 persistence modules. Because now the current algorithms that are available for computing the matching distance are restricted to 2 parameter modules, as they also use equivalence classes of lines, but these equivalence classes do not extend to parameter spaces with n bigger than 2. And well, that is it for today. Thanks a lot for your attention.
Thank you. So I would, before we get to questions, I would ask everyone to unmute themselves and clap for the speakers.
Thank you.
Right, yeah, so now it's time for questions. Yes, everybody's set to mute, so if you want to ask a question, you have to unmute yourselves first. Okay, so we have one question in the chat window. Probably I missed it, but can you explain what the same reciprocal position is?
Yeah, let's go back to the this slide. So being in the same reciprocal position with respect to a point in the parameter space means that you're really, so the line intersects okay, let's start over. We have a point U here, and we look at its positive cone. So all of the values in the parameter space that are big or equal to that point. And then we look at the boundary of this positive cone, and being in the same reciprocal position with respect to this point U means that the two lines would intersect the boundary face in the same way. I mean, the boundary of the positive cone in the same way. So yeah, these three lines are in the same reciprocal position, but yeah, if we would look at another line here, that would, so the black line here intersects now the boundary of the cone of U along the horizontal face and not on the vertical face. So they're not in the same position with respect to that point U.
Okay, more questions.
And Celia, I had a question. Very nice talk. I was curious, do you think there's a possibility to extend beyond one critical filtrations, or would that, you know, maybe not, just in the future, is that a possibility, do you think?
That is a good question. I don't know, because for now we've really used the fact that cells have to enter like at comparable comparable values. So I don't know how we would deal with this if it can enter at two different time steps. Haven't really thought of it yet.
Cool, thanks.
Oh, and then we have another question in the chat window, namely, so still related to the equivalence classes of lines. Why restrict attention to straight lines only? Any increasing trajectory would work.
Well, I think probably the objective is to look at the matching distance, which I think we really need to compute the way the matching distance is computed is to look at distances of 1D modules along these lines and then use it kind of a weighted sum of these distances, I think. And this requires straight lines. So this is, I think, one reason to look at straight lines and not curves.
I have a question. If I have the right Celia hacker, you're involved in neuroscience also?
Yes.
Does this have anything to do with neuroscience? Is this just pure topology?
No, this is just pure topology for now.
Okay, thanks.
It's a totally different group. It's a women in computational topology group, so it's nothing to do with my research group.
Okay.
Yeah.
Okay, more questions.